Good day everyone, welcome to another learning edition of MathBite and Circuitry. Today we'll be talking about how to test 5 basic electronic components using multimeter. So the 5 basic electronic components are resistor, capacitor, inductor, diode, and your transistor. Okay, so this is our 5 basic electronic component. Before we jump right in using multimeter to test our component, let us just understand first the electronic schematic symbol of our components. Okay, for resistor, the schematic symbol is drawn like this. For inductor, this is like this. For capacitor, it is drawn to be like this. This is your positive, this is your negative. We also have for diode is to be like this. This side here, it will be your anode. This is your cathode. Normally that is your positive terminal and this is your negative terminal. We also have our transistor. Okay, transistor has two types, NPN and PNP. So the schematic symbol for transistor, NPN, is drawn like this. So you have your base, collector, and your emitter. So this type of transistor is what we call NPN. So this is our NPN transistor. Okay. The other type of transistor is what we call PNP. Okay. PNP transistor is drawn to be like this. So arrow pointing towards base. So this is our collector, this is our emitter, and this will be your the base. Okay, this type of transistor is PNP. Okay, now to remember if transistor is NPN or PNP based on its schematic symbol, you can say NPN to be not pointing in. So this one is not pointing in towards the base. PNP can be remembered as pointing in. So this one is pointing in towards the base. So that's PNP. So transistors typically has 3 layer, which is you have the negative, positive, and negative, or positive, negative, positive layers. Okay, so basically that's the electronics schematic symbol of our components. Okay, now before we test our resistor, we need to understand first the color coding table in our resistor. Okay, so basically your resistor is color coded. Okay, this one right here is, if I have to read it for you, you have a color of brown, black, yellow, and gold. So that is brown. You have your black, yellow, and the last part of your band will be gold. Okay, the first color is will be your first significant digit. The black one, which is your second color, it will be our second significant digit. The third one is our multiplier. Okay, multiplier. And gold is our tolerance, or your resistor tolerance. Right? Now, to read the value of our resistor in ohms, okay, in ohms, we need to understand first the orientation or the numerical values based on the color given, or the colors that we have read here: brown, black, yellow, and gold. So I have here a sample table of our resistor color coding. Okay, so for black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and no color. So this one is our first significant digit, second significant digit, third significant digit, and your tolerance. For black, that's 0, brown 1, red 2, orange 3, and so on. Okay, for gold, silver, and no color, there's no numerical value. Same thing with our second significant digit. You have the same alignment or pattern based on its numerical value that corresponds to the color. The third color will be our multiplier, and the last color is our tolerance. Okay, so for example, let's say our color right here is brown, black, yellow, and gold. So if you have to check for the resistor color coding, brown is 1, black is 0. So that you have 1, black is 0, yellow is your multiplier, so that's times, what is yellow here? 10K. Okay, or 10,000. Alright, and then this one, which is gold, your last color, is the tolerance. Okay, the tolerance for gold is 5%. Okay, so the tolerance is 5%. Now we can use our calculator to compute this one. So you have what do you call this? 10. That's your 10 times 10,000. You have 100k kilo ohms. So we have 100. Oh, sorry. We have 100 kilo ohms. And then the tolerance is plus minus 5%. So there is normally a percentage error, can be increased to 5% or decreasing to be to 5%. Okay, so to calculate this, you just have to multiply 100 kilo ohms times 5%. So that's 100 kilo ohms times 0.05. So that's 5,000. So meaning 100 kilo ohms plus or minus 5 kilo ohms. Okay? So the value can be in the range of 105 kilo ohms for positive value or for upper value, and then you also have 95 kilo ohms for negative tolerance. Okay, so what does it mean? You can read, maybe you can read 105 kilo ohms, that's still in the range of 1000 or 100 kilo ohms, so that we can say, or we can conclude that our ohmmeter is in good condition. Okay, same thing with the 95 kilo ohms, which is in negative tolerance or negative of our 5%. If you read 95 kilo ohms, that can be considered to be in good condition, our resistor. Okay, to test this, so we can use our multimeter. So we expect to have a reading of 100 kilo ohms. Okay, so 100 kilo ohms. So I can put this into 10K as my range of meter reading, and then we can test the value. We can test the value of our resistor. So that's 10 times 10K. So that's 100K. So then 10 times 10, that's 100K. Okay, so it's in the range of 100K. So this is a good, so this we can conclude that this is a good ohmmeter resistance reading. Okay. To identify if our capacitor is working, we can use again our multimeter. So we just set our multimeter to resistance scale or reading, and then normally our capacitor, if it's working, it will give us low resistance, and eventually it will return to the infinite ohmmeter value or resistance value. So what does it mean? Once we connect our test lead to each terminal of our capacitor, it will store energy. So that signify that the value or energy is being stored in our capacitor, and eventually it will goes at rest towards infinite resistance. So it's storing and it releasing the energy. So that should give us an idea that our capacitor is in good working condition. Otherwise, if the resistance goes to low resistance and it did not deflect back to the infinite reading, we can consider that our capacitor is short-circuited or short circuit. Same thing with another condition. If our capacitor did not return or did not deflect to low resistance back to the infinite reading, or it's just at rest like high resistance, or it reads high resistance, we can conclude that our capacitor is open circuited. So the other one, low resistance, short circuit, high resistance, open circuit. Okay. To test our capacitor, it should give us, again, conclude that deflect goes back, or infinite resistance. So that gives us the idea that our capacitor is, that should give us the idea that our capacitor is in good working condition, right? So let's test. So see, it goes right there, it goes back because it's releasing, it stored the energy and it released the energy. So we can say that our capacitor is in good working condition. And the third component that we're going to test is our inductor. So remember that inductor has this schematic symbol, and this is the physical structure of our inductor. So inductor is basically a coil loop around into X number of turns. Okay, so this type of inductor is basically has actually 6 terminal, which is connected to end of this wire. The other one is connected to the other side, and then the other one is connected to the other side. So if capacitor stores energy, inductor stores magnetic energy. Now, to test if our inductor is working or in good condition, again, we will going to use our ohmmeter or multimeter. So if this if this wire is connected to the other wire, so basically that should give us low reading of resistance. Same thing on the other side and same thing on the other side. Otherwise, we can conclude that there is a discontinuity, or there is an open circuit in each end of the side or the terminals. Okay, so to begin, we're going to test this portion that should give us low reading of resistance. Okay, so that's okay, let's work. That's in good condition. Okay, that's also in good condition. So sorry, let me put this sideways. So this is also working. Okay, so our inductor is also in good condition. For diode, to test our diode, we need to learn first the behavior of our diode. There are two characteristic of diode, whether it's forward bias or reverse bias. Okay, you remember that the schematic symbol of our diode is something like this. Okay, so this one right here, this portion is our negative, the other one is our positive terminal. Okay, if I have to take a look closely of our diode, so you will find here that there is white label here, or should I say gray, that should give you an indications that this one is your cathode or negative terminal. So this is your negative terminal, this is your positive terminal. Okay, now to turn on, as I mentioned, the two characteristic of diode, it can serve as a switch, turning on or turning off. Okay, to turn on our diode, we need to put, let's say for example, a voltage applied. So if I have to put a voltage here, let's say positive and negative. So in law of magnetism, positive to positive repels. Okay, so meaning the current from negative to positive, because you connect your anode to positive terminal, it will repels. Okay, if the condition wherein the diode breaks the barrier, it will now complete the path of our circuit. So we call it barrier potential in this area. Okay, so this area is, we call it barrier potential. Okay, this should be barrier potential. Normally, the barrier potential is depending on the materials used. If they use germanium, your barrier potential is 0.3 volt. For silicon, the barrier potential is 0.7 volt. What does it mean? This is the needed value at least to turn on the device, or the needed source voltage, okay, needed to turn on the device. So let's say, for example, we have the source voltage of 3 volts here. So basically, if this is germanium or silicon, it will overcome the barrier potential, giving the condition of our diode to be in forward bias. Okay, forward bias is equivalent to on state of our diode, on state. And yeah, obviously the other condition will be reverse bias. Okay, so that can be let me say here to be reverse bias, bias, which is equal to off state of our diode. Okay, now to turn on the device, again, as I mentioned, you need to apply positive potential here, or positive voltage here, to your anode. So again, by law of magnetism, it will push or repels until such time if the barrier potential will be overcome by the source voltage, which is obviously in my case that's 3 volts. It will break the barrier potential and it will put diode into on state. Otherwise, if it's reverse in polarity, it's off state. Okay, now to test your diode, you have to use your multimeter. So you can use your multimeter in a way. By the way, my red test probe is considered to be negative, and then my black test probe is considered to be positive. So that's not all actually always the case in other brand. It just so happened that my tester here is somehow using conventional current flow. Okay, so now to test, if this is my positive and this is my negative, I have to put the anode here to be into my black, and this should gives me forward bias. So see the deflection there, so meaning it's forward bias. Okay, now if I have to reverse the situation, this should not give me an indication of low resistance. Otherwise, we can conclude that diode is defective. See? So you have two states, forward bias and reverse bias, in order to conclude that your diode is in good condition. Otherwise, if it's forward bias and then the other one is forward bias also, we can conclude short circuit. If it's reverse bias, which means high resistance, both end to end, reverse bias, and the other one is also reverse bias, we can say that our diode is open circuit. So it's damaged already. Okay, so you need to replace your diode if that will be the case. Let me just show you another type of diode, but this time around we call it LED. So this is a light emitting diode. Okay, again, as I mentioned, it just so happened that my test probe is different in terms of color codes of positive and negative polarity. So because if I have to show you, if this is positive and this is negative, that this should light up our LED, because the other one is positive, the other one is negative. So see, it's not lighting up. Okay, because my positive is actually the black one. By the way, in diode, this LED, the longer terminal is actually your anode. Okay, in my case, this is the longer terminal, which is my anode, and then this one is my cathode. So obviously the shorter one is my negative, and this one is my positive. Again, pay attention that my red one is my negative, and then my black one is my positive. So this should give us this should light up our diode or LED. See, it's lighting up. Okay, so that's give us an indication that this is in good working condition, and this is also in forward bias. Okay, so forward bias, or it's on state. The last component that we're going to test is transistor. So you will notice that transistor is a 3-terminal device. Okay, if you remember in our schematic diagram that our transistor is drawn to be like this for NPN. This is our collector, base, and emitter for NPN. For PNP, collector, base, and emitter. So this is P and P. Okay. Now, in order to analyze the way how transistor behaves, we can think about a diode, two diodes interconnected. Okay, let's say for example my diode is to be connected like this, and another diode be like this. Okay, so you remember that during our discussion in diode, if you apply a voltage potential here of positive and a negative potential here, it will create forward bias, so turn on, and the other one is turn off. Okay, now to identify if it's NPN or PNP, we need to test first or identify the pin configurations or the pin outs based on this transistor that we have here. Okay, now let's say for example, if I have to use my tester. Okay, so let's say connecting here to this one. So I'm getting a reading, resistance values, and another resistance value here. Okay, so we know that from the schematic symbol, it's obvious that our mid terminal is the base. So you will notice that their common is in this portion. Okay, so that's my base. Now we are reading two resistance values here, but in order to identify the collector and emitter, we need to set the condition wherein the base to emitter is slightly greater than the base to collector. Okay, so base to emitter is slightly greater than base to collector in terms of resistance. Okay, in terms of their resistances, terms of resistance. Okay, let's analyze again. If this is their common, which is my base, I'm suspecting that this is my base now. So I'm reading two different resistance value here, but slightly different from one another. Let's say, for example, this one is since I'm in the scale of 100, multiplier of 100, so that gives me about 400, 3, 4, maybe 450. And then the other one is, it's slightly greater than the other side. So this one is, so this one is greater than the other one. So I can say that now this one is my base, collector, and emitter. Okay, because base to emitter is slightly greater than base to collector. Again, let's try again. Base to collector, and this is my base to emitter, which is greater than compared to this one. There. Okay, let's try again. So that gives me 2, 3, 4, 4.5, 450 base to collector, may 450 ohms. The other one somehow it's like 460 ohms. Okay, so we can say that this is now my base, collector, and emitter. Now what type of transistor is this? So again, if this is my, if black will be my positive, because my multimeter is using conventional current flow. If this is my positive, I can say that this is NPN. So this is NPN. Okay, so N if this is my collector, that's my N, this is my P positive, and N, so NPN transistor. Okay, I hope this line of thought or thinking or analysis will guide you or help you in identifying the pinouts of our transistor, whether it's base, collector, emitter, and the type of transistor that we are using, whether NPN or PNP transistor. Okay, thank you.